Bismillahirrahmanirrahim. Welcome to Advanced Control System Theory. Today we are going to solve homework number 11. Uh, this is C. Next equation and obtain 0 point discrete system based on the euro and y0. So we have to calculate the value of the discrete time values. States that the 2 unit step determined is a system the plan command. Maybe this similarly in the CT that is equal to. So coming to question number 1, analytical expression for the y equal to t, the output response yt. So the A, B, C matrices. The transfer function of the system is ys divided by u of s, that is equal to C matrix times Ci minus E inverse, which is the matrix exponential, times B. So by calculating the Si minus E, putting the value of the S and the matrix A, so we have find the value of the transfer function, which comes out to be 5s divided by s squared 2s plus 2. And for the unit step, that is equal to 1 over s, and for this system the initial conditions are 0. So by plugging in the value of the u of t, that is equal to 1 over s over here, so the s cancel with this s, and the final answer comes out to be ys, that is equal to 5 divided by s squared plus 2s plus 2. Now, to find the yt, the time response, the output response in the time domain, we are taking the inverse Laplace transformation. So here, this is a 5, so we can just by a little manipulation, this is 2, and we will put instead of 2 1 plus 1, and this will become s plus 1 whole square plus 1 square. And here we can apply the e to the power minus at formula. Here we can, so this is the formula. The value of the yt comes out to be 5 e to the power minus t exponential minus t sine t. The frequency s plus 1, so here this term is equal to this term is 1, so the sine omega t, omega is here 1, so that's why sine of t. Now, question number 2 states that discretize and obtain state model with the sample time t equal to 0.1. So we are considering the same system, and here we are discretizing the system. We are just representing the system in discrete time, and this is the first order Euler approximation. So here this is the discrete time. We are having x1, that is equal to k plus 1 times t. AD, these are the x1 and x2. Similarly, VT, you have KT output values. So for the first order approximation, AD, that is equal to identity values, and the T is equal to the time is equal to sampling time is equal to 0.1. So this comes out to be AD comes out to be 0.1 minus 0.2 and 0.8. BD comes out to be 0.1, 0.1. CD, the discrete value, discrete value of the matrix for the C will remain the same as it is. So this is the system model in the discrete time. Now, question number 3 states that obtain the based on your answer for question number 1 and question number 2, calculate by hand y0 of t, and for the discrete time 0 of t. So here was again in the value of the t, which is equal to the 0.2. So it comes out to be 0.80 or 0.81, approximately 0.81 or 0.80. For the discrete time calculation, this is x1, this is the discrete time representation, x1, and this is the x10. Similarly, the initial value of the UK, that is equal to 1. For the UK and for the states value, initial states values are 0, 0. And so by putting k equal to 1, x1 0.1 comes out to be 0. This out the x1 0.1 values comes out to be 0.1 and 0.1, for which the t equal to 2. When you are having this, here is the kt, so when we put k equal to 2 and t is equal to 0.1, it comes out to 0. So just putting x1 0.1 values here from the previous equation, we are having 0.1 values, 0.1 and 0.1 x1, and these are the states value x1. So this comes to 0.1 and 0.1 here, and now multiplying these two matrices, so it's comes x here. Here this value is equal to the UK is equal to value is equal to 1. The new values is 0.21, 0.16. Now these are to find the output values YD 0.2. So this is the C matrix. We will multiply this. So the discrete time values comes up to 0.9. So for the continuous time it was 0.8, and for the discrete time the value comes out to be 0.9. Now we are having here this is the continuous time system. The first, the blue is the continuous time system, while the this is the zero first order holds, and the same time here in this command is equal to 0.1. So this is the discrete time system. Question number 5 states that determine the sample time for which the discretized model is about to be unstable. So for the first order approximation, where 1 plus the modulus value of the 1 plus lambda I of the A matrix times the sample time should be less than 1. Or in other words, if you're having the discrete time A matrix, so that the eigenvalues of the discrete matrix times the value of the lambda 1 and 2 for the continuous time. And it, so in this case, the eigenvalues are not negative and distant, but these are values are complex. The real value is -1, while the g omega part you're having a pole pair here. So we are having a to find by using the matrix exponential. This is a lengthy calculation. So here this part is coming here. This is the real part, and this is the imaginary part. And this the phase portrait plot when the value of this minus t is positive, and when it is greater than 1, so this value shows the radius of the circle. When the value of this value is equal to less than 1, so this is the stable system. And with the passage of time, when x goes to infinity, the system converges to 0. So this is a stable system. So here, when the for the discrete time system, or when this value is minus t, this is the value here. And when this e to the 1 minus t, this sampling time is equal to uh, mm, uh, 1, so it will be this system will become it will be unstable. It should be less than 1. So for t equal to 1, the system e to the 1 minus t is equal to 1 make it unstable. The value greater than equal to 1 will make the spiral system is unstable. If the system is stable, so the spiral converges to 0 as time goes to infinity. Now, question number 6, coming to question number 6, the generate a stable plant GU system order is 100 using MATLAB command random, RAND. Show clearly how you generated the plant G and the eigenvalues location in the complex plane using the MATLAB command tzmap. We will show this command to find out the location of the poles and zeros. Then construct a reduced GA with the following commands. So this is the balance realization of the G transfer function, where we will eliminate the lower value that is less than 10 raised to power minus 8. And this is the reduced model reduction. So this is the reduced GA, the reduced transfer function. So in the first case, we will find the value of the GA, the reduced model values, which comes out to be 4 here in this case. And for them in the B part says they compare the Bode plot of G and GA, the transfer function and the reduced transfer function with the model reduction. So this is the MATLAB code. We are having the PZ map of G, and here we are eliminating the values of those values which are the magnitude of which is less than e to the power minus 8, exponential to the power minus 8, the low values. We can just neglect those values, and this is the model reduction. So this is the model reduction command here, and here the Bode plot. This is the Bode plot. This is not the GVAL. This is G, and this is GA. This is the reduced model here. So this is the legend. So these are the eigenvalues here. The one of the eigenvalues is very near to 0, but it's not 0, but it is negative value. This is the value of the G and the similar. And for the C, redo part A and E with the elimination equal to minus e or minus 5. So when we eliminate those values, the P2 that is less than e to the power minus 5. So this is the model reduction. We are considering here the GBAL 2 and elimination 2. So this is the G, this is the original, and this is G as the reduced model for 0 for this value. And the value seems to be both values, the magnitude of the values is the same. However, the phase of the two systems are not the same. So this is the G, the blue response shows the original, the transfer function, and a dotted response, the red shows the reduced model. So thank you.